Hi folks, welcome to the equipment review video. This is in low budget oscilloscopes. And in this video we're also going to help describe oscilloscope basics, what some of the parameters mean to help you figure out if you're in the offing to purchase an oscilloscope, what kind of capabilities you need. So what started this? I'm getting to the point where we will become experiment heavy, meaning my research in ethereal mechanics. Okay, to support this requires networkable test equipment. Okay, networkable test equipment allows us to link together test equipment to be controlled by a PC such that it'll operate as a coherent system. And we'll give examples in a moment. And also that the PC can read the scope measurements or whatever instrument measurements, analyze them to convert them into meaningful things about what was being measured. Again, I'm going to give examples in a moment. We are going to have other videos later on other types of test equipment that I've purchased for this initiative. But right now this video is focused on oscilloscopes. This is probably going to be the first of two parts. So I have an oscilloscope. I've had this oscilloscope. This isn't a picture of my scope. It's a picture of a scope that looks just like mine. The biggest problem with this is there's no way to get data off it. I did not purchase a network card back then. Did not know why that would be needed or necessary. The idea of doing networked equipment really wasn't catching on yet. They did have the ability to put a floppy disk in there to pull data off the scope for analysis, and I thought that was fine. Didn't think about, and I even went online previously. They do sell network cards, adapter cards for this, but they want $600. They're on eBay, and I don't know if they're even working. The other issue with this is going forward, I do a lot more digital work, a lot of work with Arduinos and digital circuits going forward. And this scope does not have logic analyzer capability. A lot of the new scopes have what they call mixed signal capability, which means they have a logic analyzer, 16-channel logic analyzer built in. You can kind of use this as a logic analyzer where you can look at 4 channels of a digital circuit at the same time, but it doesn't do any address decoding and any other nifty things that the more modern scopes will do. So this scope is getting long in the teeth. It's still accurate, it still functions, and we're going to actually compare this scope to the new scopes as kind of like, this is what the old guard has, and let's see what the new guys have. Okay, so the capabilities I'm trying to replace here are as a 350 megahertz bandwidth at 2.5 gigasamples per second for each channel. Okay, and what we're going to do first is we're going to describe what these numbers mean, so that you understand, what these parameters mean as far as selecting a scope. Oh, before that, let's explain why network capability is important. Okay, over here to the right, you can see like a little tiny PC, and that's going to be hooked up to a network switch. And then we'd have a network power supply, a network high-speed function generator, and a networked oscilloscope. Some of the scopes actually now come with a little built-in function generator, but they usually only go to 25 megahertz. I purchased a separate one that goes to 122 megahertz. Okay, and because I need the bandwidth clean out to 100 megahertz to do some of the things I'm going to do. Okay, so that's why I paid the extra money for that. This was $800. We'll have another review video on this guy. I also have purchased a Siglent power supply, very nice power supply. So nice, in fact, I purchased another one because like I said, or like I will say, that I want 2 separate setups so I can have 2 sets of experiments running at the same time, because I don't want to spend time breaking experiments down, Anyway, so what we're showing here is we got a networkable power supply, networkable function generator, networkable oscilloscope. And here we might have a small circuit that may only have like 1 operational amplifier, maybe a couple of transistors, a couple of resistors, very small circuit, something you can put together in an afternoon, and you don't even have to build a printed circuit board. It can be just, very simple design. Here it's connected to measure a loop of wire, an inductor. So this small circuit's going to get powered by the power supply. And then this guy is going to inject a signal of a particular shape that's important to the means in which we're measuring. And this guy is going to take the measurements. So then this guy, he is going to then set everybody up, trigger everybody, and then pull the data off for analysis. And what he's going to do is then turn that measurement into what the inductance is that was measured. Okay, so basically what we're going to do here is we're going to create with this equipment a very high precision inductance measuring system that later on we could then build into a single Arduino circuit if we decide we want to go ahead and manufacture this on a smaller scale, because we don't need all the capabilities of this. In other words, for this circuit, we just need a simple ramp circuit or a simple, very precise step circuit, okay, which can be done with a little bit of circuitry. When the beautiful thing about this is this can be almost anything. So that gives us total flexibility, and we might decide as we're playing with this idea, hey, let's try to put let's put an arbitrary signal in there. This guy can do arbitrary functions. Okay, and then so we can do interesting different things to see if we can improve on just a simple idea without having to go build all kinds of circuitry. Okay, this guy can basically be any kind of function generator out there. It's an arbitrary function generator. This guy can supply any kind of power we need. So if we decide, hey, plus or minus 12 volts not enough to do this measurement, yeah, we just change the parameters. So this stuff gives us full flexibility. And this guy is going to take the sampling data. It's going to basically be our A to D converter, if you will. And then we're going to take the data off, and then we can analyze it to deconstrue the information to figure out what the resistance and the inductance of this circuit is. Okay, and so that's where we're going. We want to be able to construct very complex systems because these part components here can have a wide dynamic range of what you can do with them. And then what we can do is then we can figure out what's going to work the best, and then we can build a very small circuit later on, build a small box that can do that without all this equipment for much cheaper. Okay, the other thing we're going to be doing, this is just a couple examples of the things going forward. This here is a little cute little Doppler radar you can buy from DigiKey. These are the DigiKey, or these are the part numbers. You can get one for $67 and one for $108. This is the $108 one shown here. And so what you can do, this uses a voltage controlled oscillator, so you can actually make a chirp measurement with this. So we would use this guy to create a high-speed chirp. They use the frequency counter in the scope because the voltage controlled oscillator will give you a sample output that you can measure to determine what the frequency is, and also record the analog output here. And then we can do the analysis on the FFT, or we can do the analysis here. Either way, we can turn these components into a tiny chirp radar system. Because going forward in Ethereal Mechanics, we're going to make a lot of Doppler measurements to check out the flow of the ether. And these are K-band Doppler radars. They're better than the one I looked at a couple years ago, which was a Doppler radar, but it didn't have the chirp capability, which will extend our ability to measure things in incredible ways. Okay, so this is where we're going. This is why we want... so in other words, because of this equipment, I don't have to build specialized Arduino equipment for this. Otherwise, I would. I'd have to put A to D converters. As a matter of fact, one of the things going forward is, if once we get the idea of this, I believe an Arduino Do has enough processing power and capabilities that can run this thing by itself. Okay, so then we can make very tiny instrumentation that we can then put on moving experiments once we prove this concept out. So that's where we're going. That's why we need networkable equipment, because this equipment, like I said, can become components of a much more complicated measuring instrument, all tied together through a small computer to do the analysis, and then we're off to the races. So getting back to the two big numbers, this is a screenshot of the Siglent page, which shows their SDS Plus oscilloscopes. And you'll see that you can get them in different bandwidths. And in this particular set of scopes, they all sample at 2 gigasamples per second. Now we have to be careful because these numbers have to be interpreted. For the lower level scope makers do a little bit of game playing. When you get to Tektronix and Agilent, they pretty much have a separate A to D converter on each channel. So if you get 2.5 gigasamples per second, that's 2.5 gigasamples per second per channel. Okay, in Rigol, they say that it's got 8 gigasamples per second sampling. Well, that's 8 gigasamples per second if only one channel is on, 4 gigasamples per second if only 2 channels are on, and 2 gigasamples per second if all 4 channels are on. So they basically multiplex one A to D converter over all 4 channels. Now that has the benefit of basically saying you only have to calibrate one circuit. So that might actually have benefits. Okay, in Siglent, they're a little different too. They treat each one of their channels as pairs. Okay, so in each pair, if you only have one channel on, doesn't matter which channel in the pair, that channel samples at 2 gigasamples per second here for this scope. Okay, if you got both channels in the pair on, they both can only sample at 1 gigasamples per second. Okay, so you have to understand the way each scope defines what their sampling rate is. So these are a little bit of a misnomer here. Okay, but what do these things mean? What does the bandwidth mean, and what does the gigasamples per second mean? Well, we're going to cover bandwidth first. Okay. And, so the gigahertz, the bandwidth, okay, here's an example of 500 megahertz and 8 gigasamples per second. The 500 megahertz refers to all of the conditioning circuitry from the beginning when the signal comes into the port on the scope, all the way back to the A to D converter, which converts to digital. After this point, there's no more signal degradation. It's just all digital processing. Okay, so in this area here, you could have anti-static or electrostatic discharge protection components. You're definitely going to have attenuation and gain stages. A lot of scopes have bandwidth limiting filters, and other scopes will have, let's say, AC to DC coupling circuits, and there may be some other things in there I have since forgotten about. But there's a lot of things that can degrade your signal before it gets to the A to D converter. Okay, and so what does this 500 megahertz bandwidth mean? Well, luckily, somebody actually published a chart. Now, this is a logarithmic chart. Okay, this is 1 megahertz, 10 megahertz, 100 megahertz, and 1,000 megahertz. And this chart is from a scope that claims to have a 500 megahertz bandwidth. Okay, so we in engineering have defined bandwidth as the point where your signal degrades by 3 dB. So this line here is the 3 dB point, or the 3 dB knee, they call it sometimes. This is the knee here, where the signal starts to degrade. Now, what's interesting about this, at 500 megahertz, that actually passes at about 2 dB down. So this scope company is giving a little bit more margin, which is nice. Okay. Now you notice that, so this is a 500 megahertz. I drew another line here at 50% of the bandwidth at 250 megahertz. Again, because this is logarithmic, it's not halfway back, it's over here somewhere. And you'll notice you start having really serious degradation. And it's not serious really, actually. It's only, again, it's less than 2 dB to this point. Okay, but what you're seeing here is that your signal's starting to roll off, because this is what we call the 3 dB knee right here. And so what's important, other scopes, most of the time scopes don't give you a nice chart like this. In their specification, they're going to give you a thing called bandwidth flatness, and they're going to say something like, yeah, between 10 kilohertz and your bandwidth, which in this case would be 500 megahertz, over 10, you can expect plus or minus 5 dB, or half a dB rather. Then when you get from 1/10 your bandwidth to 1/3 your bandwidth, this damn mouse, 1/10 your bandwidth to 1/3 your bandwidth, you can expect plus or minus 0.8 dB. From 1/3 of your bandwidth to 2/3 of your bandwidth, this is what you're going to see. And when you get from 2/3 of your bandwidth to all the way to your bandwidth, you can have as much as 2 to 2.5. Okay, so here they're actually saying, this is actually for this scope actually, that at your bandwidth, you actually can expect plus 2 or minus 2.5, which is pretty good. According to this chart, they're well within their specification. Okay, so really, what they're saying at 2/3 your bandwidth, you're pretty good. So, but where I work, what I like to have is that my 50% of my bandwidth, in this case would be 250 megahertz, that's where I like to work behind. I like to have good flatness out to 250 megahertz. And then this is a little gimme region that we can do other work here, but we can't do the kind of work I can do here. This work here, you can expect other degradations, and we'll talk about that in a moment. Damn, I wish the mouse would stop turning off on me. Okay, so why do we care about flatness in this area? Well, when you look at signals, any kind of transmission path, whether it be the front end of a scope or a circuit, is going to have different frequency capabilities to different harmonics. Like over here, we can make a triangle wave, okay, by adding a sine wave plus a smaller sine wave plus another smaller sine wave. And if we keep adding these up, you get closer and closer to a sine wave. But you notice each one of these harmonics is higher in frequency. Okay, so to get a precise triangle wave, we need harmonics out to at least 5 times the fundamental. In this case here, they're saying 11 times the fundamental is even better. Okay, so, and here, if we add up this is like Fourier analysis or Fourier series, if you want to look this up. You know, if I want a square wave, I can keep adding up sine waves until I can get closer and closer approximation of a square wave. And the more harmonics you add up, the more closer to a square wave you're going to have. So the rule of thumb out in the industry is that you want to operate at least 5 times your harmonic. So if you want to do work with 20 megahertz triangle waves or 20 megahertz square waves, then you need a circuit bandwidth of at least 5 times that, at least 5 times that. So we'll be working up to the 20 megahertz for these what they call fundamental signals. And so we need a clean representation out to at least 100 megahertz. Okay, and the other problem that you have at the knee, which I was going to mention, you know, a little earlier, was that you also have a phase distortion. At the knee, you actually have 45-degree phase offset. So in this no man's land, you experience more phase offset than you do in the working region here. So, you know, I call this the working region. Other people might have a different specification, but in here you're going to have very flat phase response too. Because if you look at these little harmonics, if you add these up and they're shifted, that would be a phase offset. So they're not going to line up right. Instead of this little peak adding up on the peak, it may add up on the side because of a 45-degree phase shift. Then you can have a rumply triangle wave. Okay, so again, in this happy region here, I don't want any phase shifts and I don't want much amplitude distortion. So that's going to give us good representation of the signals we're going to measure back in the 20 megahertz range. Okay, we can still do work out here, but we're going to understand that we're going to have a lot more distortion. We can look at sine waves pretty cleanly out here. They're not going to be that bad out here. And we can look at, you know, simpler, you know, functions than these. And digital signals will be fine out here, basically to see if a digital signal exists. All right, but that's the key here. The key is that this area here is going to offer us the most distortion. So that's why I call this no man's land. I don't want to do precision work out here. Again, it doesn't mean you can't do other work out here. Okay, so again, we'll be making precision measurements of ramp type signals with fundamental frequencies up to 20 megahertz. Okay, this means we need clean phase and amplitude response to at least 5 times that, which is 100 megahertz. And then we want the 3 dB need to be at least 1 more octave above the 100 megahertz. So we need a scope with at least a 200 megahertz bandwidth as a minimum. We can go higher if we're willing to spend the money for it, but for our needs, we need 200 megahertz as a bare minimum. Now the next part is sampling. You know, how much sampling, like the other parameter is number of gigasamples per second. Okay, well, assume that this is our input signal here, and this is a 20 megahertz ramp signal. Well, if we do 5 times oversampling, that's going to look like this red line here. I got a dotted outline of this here for reference here. So you can see that every 5 times, for each ramp, we're going to put 5 samples on the ramp, and it's going to give us like a sawtooth. And you can see that this downward side doesn't line up exactly, so we have lots of distortion. So if we double our number of sampling to 10 times oversampling, we get a much more accurate representation of the signal. But still, for our purposes, 10 times oversampling still is probably not good enough. So we're going to have 10 times oversampling, but what we're going to do is we're going to make sure that 10 times sampling occurs out here at the end of no man's land. So if we have 10 times oversampling here, it means we're going to have 20 times oversampling in our happy region, at least over here. So that's where we want to go, at least 20 times oversampling to the end of our happy region, which is going to give us 10 times oversampling at the end of no man's land. Okay, so what we're looking at is we're looking at a 200 megahertz scope with 2 gigasamples per second. That is the minimum needs for our purposes. And these are the contenders that I looked at. We have Rigol, Siglent, Keysight, and a Siglent I was kind of considering. It's a lower cost scope, and at least on this one you can get 2 channels at 2 gigasamples per second. And I was thinking that might be good enough for our needs in an attempt to try to save money, okay? And so I looked at that, and here I'm comparing, well, anyway, so let me go over them. So the Rigol MSO 5354, all these scopes have 350 megahertz front ends. Again, I only need 200, but I'm trying to replace the Tektronix, which has 300 megahertz. Okay, now here's the sampling. On this Rigol, if I have 1 channel on, I can sample 8 gigasamples per second. If I have 2 channels on, I can sample 4 gigahertz per second. If I have all 4 channels on, I can only sample at 2 gigasamples per second. But again, that's our bare minimum of what we need. For the high-end Rigol, you can get this scope up to 1 gigahertz front end, but that's kind of pointless because they only give you 5 gigasamples per second as your top sampling. So we backed off to a 300, and they charge a lot of money. You can upgrade these if you want. They charge money. In other words, they put bandwidth limiters on all the scopes. Even Agilent does that, or Keysight. So your front ends of these scopes go all the way up to the max scope in the series, and all you're doing is you're paying to turn off a bandwidth limiter on your scope. So you're paying just to have something turned off so you can use the scope. It's kind of cheesy in my opinion, but everybody's doing it, so whatever. So in any event, this scope can go up to 1 gigahertz front end, but I don't want to pay because it's like hundreds to thousands of dollars to pay for that extra bandwidth at the input. Okay, in this Siglent scope, can sample 5 gigasamples per second with 2 channels and 2.5 gigasamples for 4 channels. So this scope is the exact replacement for the Tektronix as far as capability. The other interesting thing with these higher end Siglent scopes is they have the ability to average samples in line to give you effectively more bits of resolution, which is nice, but I don't need that because we're going to be doing a lot of processing with the computer. I can do that processing and post-processing. I don't need to pay for that feature. I can do that in post-processing. For just simple analysis and looking at stuff, 8 bits is fine. I don't know if Keysight has that. I didn't look for that. I just noticed this recently for these guys. I looked for it in the Rigol. They don't seem to have had it. I don't know if Keysight had it because I didn't go back and look after I noticed that these guys had that. Okay, but this scope here, they want $4,700 for this scope. Okay, and then you have the Keysight I looked at, and they do 5 gigasamples per second on all channels, and they want, with all the features, all the options that we're looking at, they want $13,000 for this scope. Okay, then there's a lower end Siglent where they can get 2 gigasamples per second on 2 channels, and they're up to $4,000 with all the options turned on. And then then I'm sitting there hemming and hawing. Gee, do I spend another $600 for the Siglent, over the Rigol, which I was leaning toward doing? And then I saw Rigol had a sale that if you purchase the MSO option, which is you have to purchase 2 options to turn that on, you get the other 2 options for free. And so that was the deal maker for that. And that's why I purchased that scope. Okay, but then I also just realized because I'm getting the MSO capability of the Rigol, I'm only going to have 1 scope with MSO capability. And I don't want to be like working on an Arduino project on one bench and an inductance measuring circuit on the other where I'm not using the MSO capability. So I want another scope so I can have 2 working benches with MSO capability. And I decided that I went looking for a low, and I also wanted a Siglent because I had good luck with other Siglent devices, equipment, and we're going to be reviewing some of them. And so I wanted a Siglent scope just to have a Siglent. And so I was looking, and because they had a special deal on this guy for this whole thing with all the options turned on was only $2,000. And so I went with that scope. Now, in hindsight, I didn't know this one didn't come with a touch screen. Otherwise, I would have gone up to the next level up, which would have been which they did not have a deal on. Okay, and it probably wouldn't have been $1,000 more. But so I'm okay. And the other cool thing about this scope, which nobody else has, none of the other series of scopes in Siglent have this. Rigol doesn't have it. is their screen is 8 by 14. Now when we show the actual scopes, I'll show you, it's pretty nice. It gives you more of a panoramic view, so I actually like it better. And, you know, I'm sitting there saying, oh, it doesn't have a touchscreen, but you know what? If we get good at setting things up with software, this touchscreen might not be that big a deal. So that's the second scope I purchased, and this is the second scope, the third scope in our comparison. So we're going to be comparing the old girl, the 3034 Tektronix, with the Rigol MSO 5354 to the backup Siglent SDS2204X. So that is my introduction. Let's go down to the card table. Let's just set up on my card table. Okay, here we are at the beginning of the actual scope comparison. I have the Tektronix TDS3034 here, the Rigol MSO 5354 here, and the Siglent SDS2204X over here. Now, one of the things that I kind of noticed, which is a little concerning, is that the Rigol takes a heck of a long time to come up. It's about a minute. Let me turn it on. Okay, we get the nice little glowy buttons light, and then you get that, and then all you get is this progress bar for like the next minute. And I'm like, well, what's it doing? Usually, and it's beeping. Why the beeps? What are the beeps meaning? I don't know. And I'm like, what's it doing? You kind of want to know what it's doing. Like other scopes, when they take a little while, or other devices, when they take a while to warm up, they'll give you a little list of what they're checking. Okay, both the Tektronix and the Siglent take about 15 seconds to power up. This thing takes closer to a minute. And I'm wondering what it's doing. Is it going out, trying to find a way out to the internet to phone home to say, hey, you know, there's some work going on? I mean, that's one of the things that we worry about, is industrial espionage going on. Is the scope trying to call out to let somebody else know that this is part of a network that can be hacked for industrial secrets? Okay, that's why if you work for a lot of major corporations, they will not let you use scopes that are not made in the United States, or at least a country that, you know, we're on really good terms with. Now the Siglent, again, turns on in about 15 seconds. And what I love is I love the glowy buttons. Even the button here that turns a different color. Now, there's three things in the world I love, and one of those things is glowy buttons. They're all over Star Trek. They're all over 2001: A Space Odyssey, you know, where they push the button and something interactive happens. But I guess the new glowy button kind of is the touch screen, where you touch the button and you get something happen. So that's kind of like a glowy, but it's an interactive button that does something when you hit it. Okay, now I like them on the panel because it makes the panel brighter. The glowy buttons are easier to read in my older eyesight, and it's kind of a real quick thing, so I know what's turned on the right, because anything you turn on, the glowy button is going to turn on for you. Kind of give you, and it gives you a little beep, nice little tactile beep. Now I'm going to turn all the channels on. Okay, I'm going to do this for all the scopes. And what I like about this scope, as opposed to the Tektronix, both of these scopes have the advantage over the Tektronix, is they have a separate scale button and vertical position button for each channel, which is nice. Okay, the Siglent, I mean the Rigol has that too, and the Tektronix doesn't have it. So every time you want to change the scale of a trace or move it up and down, you have to select that channel first, which is kind of a pain in the neck. Okay, so again, the controls are much nicer laid out on these two guys. I guess because after a while people get sick and tired of having hit the button, so I think everybody's going that way, because I think even Agilent has that configuration as well. Now I'm going to turn all the traces on all the scopes, because what we're going to do is we are going to do an auto setup. See how good these scopes are at auto setup. So I've got all the channels turned on all the scopes. It's pretty random. Okay, for this first test, what we're going to check is see how well the auto setup works. What I have for each scope is I have their first channel hooked up to the probe compensator, and the second channel is just sitting in free space, not grounded, and the other two channels are not connected. So let's see how well the Tektronix does. All right, that's decent. I mean, it should have known that the other two channels here were not used. I mean, this was a new feature back then, so I don't really expect this to work that good. Again, I got to select the channels I don't want. So now if I turn the channels off that we don't have, will it set up better? And it does. So that's okay. That's pretty decent. So let's see what the Rigol does. And I got to look, because the auto setup is in a different place on every scope. So that was good. That identified that the other traces were off and it shut them off. That was much smarter. And let's see what the Siglent does. And their auto setup, instead of being a blue button, everybody else, their auto setup button is black. And so when I first did this, I was clicking this button trying to figure out why it wasn't working. The Siglent auto setup is a blue button up in the upper right hand corner, which is actually a nice place to put it. Okay, so the Rigol wins the battle of proper setup. This is not proper setup because these two channels aren't here. And if I do auto setup again, will it work right? It's a little better. I would have done rather what these guys did, instead of superimposing them, have them top to bottom spaced out. So the auto setup on Siglent isn't that good. Although the other thing about it is locking to the smaller signal. It should have been locking to the bigger signal. Why it's locking to the smaller signal, I don't know. That's not the signal I would have locked to, because this signal, this pink signal, is way down low in the millivolts range, and this yellow signal is the probe compensator. So that would have been the big signal I would have locked to. The other guy is locked to it. So as far as automatic setup goes, the Rigol did the best, Tektronix did the second best, and Siglent it's not that good. But I mean, that's not a showstopper. Okay, let me set up for the next test. Oh, what I'm going to do now is I'm going to compensate the probes. I'm not going to go through how to do that. I'm just going to, you can go look online for those people that there's videos on how to compensate probes. Okay, before I get to the next test, one of the other things I want to show you is, the other thing I just noticed is, if you look very closely at the Tektronix scope inputs, you notice behind the BNC connector they get all kinds of little, looks like gold, like a circuit board back there. This little ring of gold around the outside with the little segments. Okay, that is circuitry that actually connects with the probe so that the probes can be identified and or powered. Okay, and so what happens is, if I select this probe, let me show you. You see that it says that the probe setup here says only one time. Let me zoom in close. See, it says probe setup is a 1x probe. So if it doesn't detect this probe, it goes back to a 1x setup. The minute I program this in, because this little adapter thing here, this little contact, it automatically changes to a probe setup of 10x. Okay, Rigol does not have this. So for Rigol, you have to make sure your probe setups are set by you. Okay, you got to make sure that's done. Siglent does look like they have copper behind it, and let's see if that works. Let's pull out one of the first probe here. And to put up the menu for probe 1. Okay, I'm going to plug the probe in. See that automatically adjusts. Okay, I don't know if you saw it, but the probe setup went to a ×10 probe. Okay, so both the Siglent and the Tektronix gives you what I'm going to call interactive probes. I don't know if that's active probes, but at least they take some care of trying to identify what the probe type is that's connected. Okay, the Rigol does not have that. You would think Rigol, this being an upper level scope, would have that feature, but it doesn't. So let me get on with the next test. Okay, for this next test, we basically have one channel on, and we basically have the probe grounded to the ground strip, or the ground clip. Okay, the setup of the scopes are all the same. They're being set to 20 megahertz bandwidth limit, 10 millivolts per division with a 20 megahertz bandwidth limit. And the time base is either going to be to 40 microseconds or 50 microseconds. The other scopes can do 50 microseconds. The closest the Tektronix can do is 40 microseconds. The purpose of this test is to get a feel for what the noise floor of these scopes are. All of the scopes are set to 0, 0, and you can see on the Tektronix that there's about 3 millivolts of noise fuzz, and it's riding about 4, maybe 3 millivolts off the 0 mark. So we have a little bit of a DC bias and a little bit of noise. It's all in the millivolts range. Because remember, each box is 10 millivolts high. Okay, now, again, just remind you of something else. See how the squares, the grid patterns, are nice and square? I like when the grid patterns are square. This layout of this scope, this little side thing here, is a traditional layout of 8 by 10. So you have 8 gradients vertical and 10 gradients in the horizontal, and the gradients are pretty much square. Rigol is doing what everybody else is doing now, and their grid layout is 8 by 10, but you see they're not squares, they're kind of stretched out. But now going back to the other thing, look at this noise. There's at least 12 millivolts of noise and about 5 millivolts of offset downward. Okay, this scope is a noise-a-palooza. I mean, this is really disappointing. The level of noise on this scope is really disappointing, considering this is supposed to be a high-level scope. And the Siglent, like the Tektronix, oh, by the way, this scope, look at the 8 by 14 grid. I like this layout better. It gives you a much more of a panoramic view of your pattern. So I like this 8 by 14 layout. So you got 8 gradations vertical, 14 gradients in the horizontal. That's just a personal preference, my friend. I wish I could get the other scopes to have a setting where you could change it to be an 8 by 14, get that panoramic view. But anyway, going back to the noise performance, the Siglent is behaving very well, considering it's a low-end scope. It's got maybe 4 millivolts of noise and maybe 6 millivolts of offset. Those are things that are, very respectable for the amount of money I paid for this scope. So that's very respectable. In this test, we're looking at low signal. What we have is all the probe tips connected together and all the probe grounds connected together. So basically what we're looking at is we're just looking at the RF signals that are hanging in the air. So these things are basically acting like little antennas, picking up whatever electromagnetic interference is in the air, which is mostly going to be 60 hertz with maybe a little bit of TV noise or other things like that. And so we have the Tektronix here set up so that it's 10 millivolts per division, 2 milliseconds per division on the horizontal. High frequency reject is on the trigger. Trigger is the rising slope, and we're trying to trigger on this little sharp edge right here. Okay, and you can see the Tektronix, and I'm going to zoom in a little bit here. The Tektronix is very stable. And look at the frequency. If you look at the frequency that it's saying it's about 60 hertz. And the stability of the frequency measurement is pretty good. Occasionally you'll see a 61, and occasionally you'll see a 68. I mean a 58 rather. But it's pretty rare. Pretty much it's 60 or 59 and change. Only occasionally will it go out of that range. Okay, so I can say pretty much it's stable to 2 decimal places. I mean not to 2 decimals, to 2 digits. Okay, let's look at the Rigol. There we go, our noise-a-palooza again. I got the frequency counter on the bottom. All the same settings. Pretty much a useless oscilloscope, at least for small signal stuff like this. The frequency stability is not bad for the measurement, but I just saw a 65, another 65, a 70. So because it can't trigger that well because of all the noise, it's not able to get a good frequency measurement. The Siglent is doing pretty much as good as the Tektronix is. The frequency measurement, fortunately, they have a little tiny one up here, is the much better behaved of all three of them. It looks like it's stable to 3 digits pretty much all the time I've been looking at it, which is very nice. Now, the signal has a little bit of spikiness. It's got good signal integrity like the Tektronix, except you see the little spiky spikes on it. I think that might actually be on the Tektronix, but because it's got such an old display, it might not actually be visible. So I turned the persistence on the Tektronix, so they're getting little spiky spikes too, because that's what's filling in and making it flat. All those little spikes are adding up because I turned the persistence to infinity. And so it's getting fat, okay, over here. So those little spikes are there on the Tektronix. It's just not able to see it on the display. And I'm going to show you what I'm going to do for the Rigol, for the Siglent, is I'm going to turn the persistence on as well. And let's set the persistence to, where was it? Persistence, set to infinite. Okay, so you can see the persistence is now filling in, just like the Tektronix is filling in. Okay, so it's doing just the same thing. The Tektronix has a different way of handling the persistence. But actually, I like the Siglent better. It's doing a better job with the persistence because you can still see the original trace. And I think you can turn the persistence up. Ooh, let's turn the color gradient on. Oh, that is cool. I don't think the Tektronix, I'm sure Rigol has that feature. Let's see if the Tektronix has that feature. No, I don't think this has that feature. I'm not talking to you, cat. You're being a pain in the butt. Well, anyway, I could play with it, but that color is a pretty cool feature. It doesn't look as good in the camera as it does in real life. It's kind of washed out looking in the camera. What I'm seeing is I'm seeing a purple trace with cyan. That's better. That's about what I'm seeing. I wish this thing would focus better. So you get to see what's happening now, and the persistence is allowing you to see what's happened in the past, like a history. So that's one of the really cool things of these digital phosphoroscopes. But unfortunately, we can't probably do that with this guy because he's got so much noise on his fundamental signal, it probably won't even look halfway decent. Let's see if we can turn his persistence on. Display, persistence, infinite. See, his touchscreen isn't working so well. Oh, it just caught it that time. Now let's use the color scale. You gotta have a different color scale for this. Color grade. Oh, there we go. Okay, so you can see that because he's got the noise on the fundamental trace, it's actually, you know, it's just filling up the screen with dots, where this is actually probably giving me a much better history. Also here, you can see how the 8x10 color grid gives me almost 2 full traces, where these guys only have the 8x10. I mean, this is the 8x14 grid, so I get a much wider view of the signal, which is nice. Compared to these other guys that only have 8x10 grids, I only get about maybe 1 cycle. And here, oh, he lost track. I get about 1 cycle. In this section, we're going to evaluate the scope's abilities to measure a signal. I have the Tektronix AFG310 set up with a 3 megahertz sine wave with a 1 volt peak amplitude. And this, for some devices, when you specify the peak or the amplitude, some devices that's peak to peak. More normally, this is the peak value. So the peak to peak value should be 2 volts. So let's look at the Tektronix. We have all the scopes set to 500 millivolts in the vertical and 200 nanoseconds in the horizontal. Well, except for this guy, he is now 200 nanoseconds in the horizontal. Okay, and he's measuring the frequency to be bouncing around a little bit, but looks like he's good to about 2 digits. So, I mean, that's okay. These old Tektronix scopes, these features for measuring signals were put on kind of, I think, as an afterthought. They've never been really that accurate. And the peak-to-peak voltage is bouncing around between 210, 212, 209, and 212. Okay. I'm sorry, 2.09 and 2.12 volts. Let's look at the Rigol. Now, what I like about the Rigol is their frequency counter comes up nice and big, but there are other little measurement devices, kind of like these tiny things. I'm trying to figure out how to make it bigger so it's easier to see in the camera. And they're showing that their amplitude is bouncing around 2.1 to 2.15. Okay, their frequency is really good. They're off by 2 hertz, negative, but they're pretty stable. Siglent frequency, which they got the little frequency counter up on it's off by 2 hertz in the positive. So they're bracketing what the Tektronix is doing. I'm pretty sure the Tektronix frequency base on this thing is in very good shape. I mean, because the Tektronix allegedly on this scale is good to 7 decimal digits. So the amplitude I don't think is specified as that accurate, but that's okay. And the little amplitude peak to peak is very stable at 2.16 volts. I like how stable that is. It doesn't bounce around. All the other guys are bouncing around. That's nice and stable. Gives me confidence when it's nice and stable like that. Okay, this ends the evaluation that we're going to do this time between the Rigol and the Siglent scopes. We still have to do evaluations for high frequency and for mixed signal operation as well. I'm sure there's other features of these scopes I'm going to learn about as time goes on. And I want to thank my Patreon members because their funds helped made the acquisition of this equipment possible. And hey, Siglent, if you want me to evaluate your top-of-the-line SDS5 series scope, if you want to send me one with all of the things turned on, I'd be happy to take a look at it. As far as I'm going, I'm leaning toward that the lower-cost Siglent has much cleaner small signal capabilities than the Rigol has. I'm not saying the Rigol is useless. It'll probably make back its money and make back its capability when it comes to mixed signal because it does sample at a higher rate for the high-end signal stuff. But it looks like I'm probably going to be picking up another scope, and it will probably be a Siglent, unless Siglent wants to donate one. Hint, hint. Again, I want to thank my Patreon folks for helping make this acquisition possible. I was able to buy scopes, more equipment than my personal budget would have allowed for. And I could not have done it without them. And I appreciate everything immensely. And this is just going to help us get to the finished goal faster. Thank you all.